All right. Well, thank you for bearing with us and watching that video clip. Erastus, you did a great job on that. You did mention, Erastus did mention in that clip that we had some Aeromag flowing. Now I'd like to turn this over to Lo to be able to walk through what his company undertook and talk a little bit about some of the product that resulted from it. Over to you, Lo.
Thanks, Todd. Appreciate it. I'm Lo Harker, CEO of Flightec, and just want to thank eTech for the opportunity to present this data on this platform. So as mentioned previously, towards the end of 2023, we conducted an aeromagnetic survey over 3 distinct regions in the Eureka project for eTech. The survey was conducted with a drone-borne magnetometer, and the aim of these tests were to furnish eTech with a magnetic data set of high resolution for them to be able to test whether there's a correlation between the magnetic structures that they see and the mineralization that they're looking for. So in this slide, I'll just briefly cover who we as Flightec are and what we do. Then we'll move on to the approach we followed with eTech and how that survey panned out. And we'll have a brief look at some of the data that was generated during the survey. Next slide, please, Todd. Okay, so who are we? Well, we've been doing exploration since 2019 when we conducted our first aeromagnetic survey. We've branched out specifically focused on drones. We do magnetic and radiometric surveying. And as of late, we're trying to echo what we do above ground, below ground, and we've also incorporated some downhole drill logging, focusing on magnetic and radiometric data. So we identified in Namibia specifically and in the Southern African region that there's a need for higher quality survey data on smaller scale. That doesn't necessarily always mean that you can mobilize a helicopter for airborne survey, and this is typically where we come in. We believe that drones is the way forward, not necessarily manned aviation. And we focus on small to medium-sized projects, but all projects are relative, and drones are parallel scalable. So yeah, size is but a number. All of our drones operate autonomously, but we are fully compliant with the civil aviation regulations to be able to perform these surveys in manned airspace. As I mentioned, we started in 2019. Some of our memorable projects are specifically the Kunene Region project. This has been ongoing since the end of 2019. We've flown over 5,000 flying kilometers there, focusing on magnetic and radiometric data. It's over 8,000 hectares. Grootfontein was also worth a mention, not specifically for the interesting geology, but rather for the administration that was involved. Grootfontein is home to the Namibian Air Force, and typically the entire region around is restricted airspace. So it took some doing to get flight approval to operate unmanned drones in military airspace. Next slide, please, Todd. So why do we believe drones is the way forward? Well, I mentioned briefly that the drones fly autonomously, but what should be mentioned more, what should be pronounced more significantly is the fact that your proximity to source increases the magnetic response that you have. So with drones, as compared to manned aviation, we can fly closer to the ground. Compared to landborne surveys, we can cover greater areas. The drones are parallel scalable, so currently we can possibly operate up to 3 drones per team in the field. In future, we hope to have entire drone swarms that are capable of doing this mapping. Your proximity to the ground and your consistency in your flight envelope resolves to higher resolution data that can be generated, which in turn will be beneficial to the clients. We also have a small operational footprint. On the image on the right-hand side, you can see there's 3 vehicles and 1 drone. So 3 vehicles. We only typically require 1 vehicle. The other 2 were there for promotional material. Our operation is rapidly deployable, and typically we've got a small environmental footprint. And the whole focus for us is if we can generate higher quality maps, it can mean a more effective drill program, and that can mean less disturbance to the environment as we see it. And then, a big one is obviously the reduced operational risk. You can imagine the drone is lightweight as compared to manned aviation, and seeing that it's flying lower, if we were to have an accident and the drone comes down, the damage would be much less significant than it would in a corresponding manned survey. So there's a list of some of our other services. I won't go into detail on that. Todd, you can move on to the next slide, and we can start with the Eureka project and specifically what we did there. So all of our surveys typically start with a topography map. The reason we require a topography map is, I mentioned, we're flying low ground clearance. So we need exact maps of where all of the obstacles are that we plan to fly. On the right hand, you'll see a DSM. This is a digital surface model. Notice the trees in the riverbeds. These are potential hazards for such a survey. The drone will typically follow the terrain down into the riverbed, and as luck would have it in Namibia, all of the riverbeds that have trees in, the trees are quite large there. So as part of our survey, in order to generate the topography map, we use a fixed wing VTOL illustrated on the left-hand side. This is a small plane equipped with a high resolution camera. It surveys the entire area and takes subsequent pictures of the area. These pictures are then stitched together for a high resolution photo that's also rectified. And then together with the DSM on the right-hand side, we also generate a DTM. A DTM is a digital terrain model. It is similar to the DSM, but all of the foliage has been removed. Todd, you can go on to the right. Next slide, please. So using the DTM, which would represent the ideal flying surface, and the DSM, which would represent all of the hazards that we're trying to avoid, we can take the drone's flight envelope into account and generate a flight path. The image on the top of the screen will actually show you a flight path that was done over one of the 3 Eureka regions. This flight path specifically is zone 1 to 4. You'll see the drone dip down into the riverbed while still avoiding any obstacles that might be in its way. Additional optimization of the flight route that we do is we look at the drone specific flight envelope, specifically acceleration and velocity curves. The reason for doing that is you'll see in the next slide, the magnetic sensor is suspended beneath the drone. So if we don't manage the acceleration and the velocity of the drone, the magnetic sensor can swing forwards and backwards, which will induce additional noise on the system. So on the right-hand side is a typical setup of a one-man operation in the field. We usually send an assistant as well, as it does get lonely out there. This system is an optically pumped magnetometer. The Eureka project was quite a flat area to survey, so we selected a maximum flight velocity of 10 meters per second for the drone. The high sample rate on our sensor allows us to generate a sample or a magnetic measurement every centimeter down the line. This is significant oversampling down the line, but it does afford us the opportunity to apply additional filter techniques. So if there is noise present in the magnetic measurements as the sensor moves beneath the drone, then we can compensate for this. In terms of magnetic processing, processing is standard and similar to airborne magnetics. We do diurnal correction, IGRF, and as I just mentioned, we've got an attitude compensation where we compensate for any movement between the sensor and the drone. The data is then leveled, micro-leveled, and gridded into a final product. So onto the next slide, and we'll see how these grids typically look. Over here, you'll see a TMI grid. TMI means the total magnetic intensity. It is the strength of the magnetic field as measured by the sensor. The left-hand image is a regional TMI field supplied by courtesy of the Namibian Ministry of Mining and Energy. I've overlaid the 3 areas that was surveyed for the Eureka project on this slide, on this image. The middle image and the right-hand image are extracts from the bottom left zone. This is referred to as zone 1 to 4. On the center image, I've rescaled the color bars to coincide with the scaling that was applied to the drone-borne images. So what you'll notice here on the TMI field is that there's this significant more resolution in the drone-borne TMI than the regional TMI. The reason for this is that there's a tighter line spacing on the drone TMI. The drone was flown at 25 meters, and the drone's also flown closer to the ground as compared to the regional TMI. But what is nice to see here is that the magnetic highs of the regional TMI and the magnetic highs of the drone TMI coincide. Here to get more detail. And if you use your imagination somewhat, you can imagine that there are northeast trending magnetic high dikes associated with it. But luckily, we don't need to use our imagination. We've got additional processing techniques. So if we go on to the next slide. On this slide, we've applied 1VD. So this is the first vertical derivative of the magnetic field. Basically, what it does, it removes any long wavelength features and emphasizes the shorter wavelength features and features that are close together. So here on the right-hand side with the drone 1VD, you'll clearly see that these magnetic highs are in fact ridges that link along. And if you further look into it, you can see that there are actually northwest facing dikes as well. But yeah, noteworthy on this is that had you used the regional data or lower quality data for a drill plan, you might have completely missed the magnetic anomaly you were trying to target or trying to miss for your drill plan. We can carry on to the next slide, Todd. So on this slide, we can see an overlay of the magnetic data as gathered by Flightec, the 3 areas of interest, overlaid on the historic data from ETEC. There's also some magnetic high and magnetic low dikes as mapped by ETEC. Just need to note that the data on this specific slide is not TMI or 1VD, rather this is an RTP data. So RTP means it's reduced to pole. Quite simply put, it's accounting for the Earth's magnetic field and the offset the Earth's magnetic field has on our data. So we remove this offset, and it means that the colors or the magnetic highs and lows coincide with the source. So they're now shifted to be located directly above any sources that might be generating them. At this point, Todd, I think I'll hand back to you and you can go into more detail of what your plans are and if we've managed to find any correlations between your mineralization and magnetics thus far.
Thank you very much, Lo. That's an excellent summary of your activities. This slide here shows some of the historic interpretation on the dike, the presence of dikes, and you can see this in the black lines. This existed prior to this high resolution magnetic data being collected. And what I find encouraging when I see this is there is a correlation. As Lo said, we don't have to rely simply on our imagination. We have a lot of information available to us. This, all of these results are fairly recent, and we're in the process of evaluating the data, correlating the different data sets, and coming up and proofing what our exploration concept is. When you look at this slide here, you can identify features that were previously not targeted for drilling, and we now need to be able to go back, do our analysis, look at some inversion modeling of the magnetic data, take the drill traces, and really very closely, point by point, try and develop or validate this exploration model. This is encouraging, but we still have a lot of work to do. The work with Flightec, combined with the regional geochem data that we now have, builds on the initiative that started in early 2023 with this move towards optimizing our exploration efforts by utilizing technology. When the ETEC team brought in the use of the X-ray fluorescence tool to be able to help us get near real-time results in the field. So building on this, and again, I want to emphasize, we are still in the process of analyzing all this information. The geochem program itself finished up on December 22nd or something like that. So it's still in the process of getting cleaned up, and the data sets are getting cleaned up and being analyzed. But if you look at the data now, the regional geochem data, one can postulate that there has been a migration of material on the surface over time. And that migration primarily goes from northeast down towards southwest, which makes a bit of sense. When you then take the new AeroMag signatures that we're seeing, and if you agree that this data or detritus has migrated, then one can start looking a little bit to the northeast of where the big signatures from the geochem data are. Again, we're fortunate that we have drill data from the central zone and other areas where we can rebuild and reconstruct some of these situations and validate this model.